Hello there and welcome to the GCSE revision videos. Here we're looking at accuracy calculations. Let's just jump straight into a question then. So here we've got y equals 1.8 to 1 decimal place. Calculate the lower bound for the value 4y plus 1. So what you need to do is you need to kind of think about what could y have been before it rounded to 1.8 to 1 decimal place, and try and think about what the lowest value 1.8 could have been. So I'll pause the video now and give you a chance to have a go at this question. Okay, so if we think about what 1.8 could have been before it was rounded, the maximum it could have been was anywhere up to 1.85, not including 1.85 because that would have rounded upwards, but something more like 1.499999999, what we'll basically call that 1.5. And the lowest it could have been was 1.75. As long as it went down to 1.75, it would still round upwards to 1.8. So for example, 1.76 would round up to 1.8, 1.77 would round up to 1.88, 1.79 would round up to 1.8. Any number in between these two values from here to here would round to 1.8 to 1 decimal place. More accurately, this could be written as 1.75 is in between or equal to 1.8 or less than 1.85, but don't include 1.85, just include everything that's ever so slightly less than it, so 1.8 is in this region. If we're looking for the lower bound, we can say that LB, lower bound, is equal to 4 times 1.75 plus 1. 1.75 is the lower boundary for 1.8, so then we have to calculate this thing here. We're told to do that in the question. So grab your calculators now. It's going to be 4 times 1.75, enter, plus 1 equals 8. So 8 is the answer to this question. Okay, let's move on to the next one. Slightly more difficult, this next one. Give it some serious thought here. Pause the video and give this one a go. Okay, let's just carefully consider the calculation of 12 divided by 2, 12 divided by 3, and 12 divided by 4, and let's see what happens. 12 divided by 2 is 6, 12 divided by 3 is 4, 12 divided by 4 is 3. And you can see here, the lower the number on the bottom, the bigger your answer is going to be. So if we want to find the upper bound of D, we need to make the lower number as small as it could have been. So, D equals, if we're trying to find the upper bound, well, we still want to divide by as much as possible. We still want our first dividing number to be as big as possible. That's going to be 99.75. Yes, I know it can't be 99.75 exactly, but it's just anything less than it. Even the smallest minuscule of a number less than it will be correct 1 decimal place. 67 correct to 2 significant figures. Well, if we're trying to make that as low as possible, that's going to go down to 66.5. Then let's do the calculation. So grab your calculator then. 99.75 divided by 66.5. That gives us an answer of 1.5. And there we are. So when you're doing an upper bound of a fraction, the answer is the upper bound of the top number divided by the lower bound of the bottom number, because if you divide by a smaller number, you get a bigger output. And the other way round for lower bounds, if you're trying to find the lower bound of a fraction, it's lower bound divided by upper bound, because if you're trying to make the answer as small as possible, it's a good idea to divide by as much as possible, the higher number to divide by to make the final answer as small as possible. Okay, let's move on to the next question. Pause the video and give this one a go. So, in this calculation, we're looking to find the upper bound. So, UB is going to equal, it's a fraction, so we're going to want the upper bounds on the top and the lower bounds on the bottom. So, the upper bounds of 26.2 correct to 3 significant figures will be 26.25. That will be the upper bound for the top number. we have to go to, when it's to 3 significant figures, we always have to go to 4 significant figures, making sure the fourth one is a 5. And virtually the same for this one here. If we want to 2 significant figures, we have to write down 3 significant figures and then make sure the third one's a 5. So in this case we want the upper bound, so we want the lower bound of this number, so that's going to be, oh sorry, we need to square the u number, don't we? So it's this thing squared divided by 2 times 4.25. So you can see here the number for u I've chosen is the upper bound, and the number for a in this formula is the lower bound. Upper bound, lower bound. So let's just type this all into the calculator all in one go. Make sure you're good at your calculator typing skills. You're all good at technology, I imagine. You've come to this video, so I'm sure you'll be fine. And the answer is, right, we have to write out 6 significant figures. It's going to be 81.066, that's 1, 2, 3, 4, 5 so far, 17, so that's going to be a 2 afterwards. So this is the answer to 6 significant figures. Okay, let's move on to the next one. Pause the video and give this one a go. Okay, so a metal cube has sides of length 4.5, correct to 0.5 centimeters. The cube is melted down and the metal is used to make small spheres. Each sphere has a radius of 3 millimeters, correct to the nearest millimeter. Work out the greatest number of spheres that could be made for the metal. So this is a tough question. So we're going to work out the upper bound volume for the cube first. That's correct to the nearest 0.5 centimeters. So if it's correct to the nearest 0.5 centimeters, the upper boundary would be 4.75. If we've got 4.5 correct to the nearest 0.5 centimeters, then its lower boundary of 4.25, upper boundary 4.75. Otherwise, if it was anywhere outside of this range, it would be in a different 0.5 centimeter section. If it was 4.25, it would be in the 4.0 section. If it's 4.76, it'd be in the 5 centimeter section. So it's going to be 4.75, and then the volume of a cube is just you cube the number. So 4.75 times to the power of 3 rather, and that gives us an answer of 107.171875. Now if we want to make as many cubes, so as many spheres as possible, we want to make the cubes as small as we possibly can. So the lower boundary volume for the sphere is going to be, well, for a sphere, the formula for a sphere is if you've got the radius, the formula is 4/3 pi r cubed. So this is going to be 4/3 pi. And if we want to make the spheres as small as possible, we'll just work at the limit of it. We're going to make it 2.5 millimeters wide, the radius. So then we need to cube that. So type that all onto your calculator. Use the pi button, times pi times 2.5 cubed. And the answer to that is 65.44984695. So now if we want to make as many as many spheres as possible, we're going to need to divide one by the other. So it's going to be 107.171875 divided by 65.44984695. So type that big long thing out onto the calculator, 171875 divided by 65.44984695, and we get 1.637. So the question is, work out the greatest number of spheres that could be made from the metal. The greatest number of spheres is 1. Okay, so there we are, that's the answer to that question. Okay, let's move on to the next one, pause the video and give this one a go. Okay, so let's work out this question then. So there are 1,300 sheets of paper, correct to the nearest 100 sheets in a pile. Each sheet is of equal thickness. The height of the pile is 160 millimeters, correct to the nearest 10 millimeters. Calculate the upper bound in millimeters for the thickness of one sheet of paper. So if we want to calculate the upper bound, we're going to have to calculate the upper bound of the height of the pile divide that by the lower bound of the sheets of paper. Okay, so the upper bound for the pile of paper is going to be 165 millimeters divided by 1,250 to the nearest 100 sheets. Yeah, that's right. So then let's do 165 divided by 1,250, and that gives us 0.132 millimeters high per sheet of paper. And there we are, that's the answer to that question. Let's move on to the next one, pause the video and give this one a go. Okay, so in this question here we have a box, and it's the shape of a cube, 11.5 centimeters, correct one decimal place. A solid spherical ball has radius 5.1 centimeters, correct to the nearest millimeter. The ball is placed inside the box and the box is closed. Work out the upper bound for the volume of the box that is not occupied by the ball. So in this case we're going to have to do the upper bounds of the box subtract the lower bound of the ball. So the upper bound of the box is going to be 11.55 centimeters. Oh, this is a cube, isn't it? So it needs to be cubed. So if we're working out some space, it needs to be a volume. And then the 4/3 pi r cubed for the sphere. Now the sphere has a radius 5.1, so if we're trying to make this as small as possible, it's 5.05 cubed. So we've got the volume of the box, take away the volume of the sphere. Let's just do each part in turn, because then we're showing all of our working. 15 nearest whole number, so 1540.798875. Take away, and then let's do another calculation, 4/3 times pi times 5.05 cubed, and that would be 539.4643421. So let's now do the subtraction. 1540.798875, take away answer value. And the answer there is 1001 centimeters cubed. And there we are, that's the answer to the question, to the nearest whole number. Let's move on to the next one, pause the video and give this one a go. Okay, so this is the first question where we see the term suitable degree of accuracy. So let's go through some calculations to show how we do this. So we need to first work out the lower bound and the upper bound for both of these calculations. So the lower bound calculation is going to be 1/8 times, now the lower bound of C, where C is this number here, will be 10.85. This number needs to be cubed because it says cube it in the formula. And the answer to that, when we type it into the calculator, is 159.6611406. The upper bounds calculation will be 1/8 times the upper bound of C. C is 10.9, so that would be 10.95. And that would be cubed as well. And the answer to that is 164.1165469. Now what we need to make a mutual decision on is a number to a certain amount of significant figures that will round both of these numbers to that answer. So let's start first by saying 200. 200 to one significant figure would apply to both of these numbers, because if we look at the second significant figure in both, they are round upable numbers from 159 to 200 and 164 up to 200 as well. So we could say that's an answer. We could do better though. We could say 160 to two significant figures. That would apply to both of them. Because if you look, in the third significant figure place we have a 9, so 159 would round up to 160, and 164, the 4 would keep it the same at 160 as well. So that would apply to both of them, and this is more accurate, so we'll now delete this one. But what about three significant figures? Three significant figures for the first one would be 160, so three significant figures. But for the second one, three significant figures would be 164 to three significant figures, which is not the same for both of them, so we can't use this one either. And any other more significant figures, we'd have two different answers for the two different values of the lower bound and the upper bound. So the answer to this question is 160 to two significant figures. We've chose the suitable degree of accuracy. The suitable degree of accuracy was two significant figures, and it does say work out the value of D as well. So D equals 160, and the suitable degree of accuracy is two significant figures. Okay, let's move on to the next one, and another question where we get to practice our suitable degree of accuracy question. Pause the video and give this one a go. Okay, so in this question we need to work out the lower bound and the upper bound. So let's get started on the lower bound. We need to choose the lower bound for the square root of s. S is this number here. So the lower bound is going to be 3.465 to three significant figures. I'm going to divide that by the upper bound of this number, because when we want to create a lower bound, we want to be dividing by as much as possible. So 1325. And let's do the upper bound calculation as well while we're here. 3.475, because that's the upper bound of the numerator, divided by the lower bound of the denominator. So 8.1315 will be the answer to the lower bound. So let's type that all into the calculator. Fraction button square root 3.465 divided by 8.1325. And the answer to that is 0.2288903839. And let's just change the 6 for a 7 and then the 2 for a 1. And the answer to this one is 0.22924864243. So let's now decide on a mutually agreeable decimal that can round both of these numbers to that decimal and to a suitable degree of accuracy. So we could do 0.2 to one decimal place. That would be absolutely fine on both of them. But we could probably do better. We could probably do 0.23 to two decimal places on both of them. Because if we look in the third decimal place, we have an 8, that would round the 2 up to a 3, and we have a 9 down here, so that would round the 2 up to a 3 as well. But we could probably do one better. We could probably go to 0.228 to, 229 rather, to three decimal places, because if we look in the top one, the fourth decimal place will round that 8 up to a 9, and in the fourth decimal place, this one, it's a 2, which will keep this one the same. And this is as high as we can go. If we were to go to four decimal places, this would be 0.2289, and this one would be 0.2292, which are different values to four decimal place. So this here is the answer to this question, 0.229 to three decimal places. Let's have a go at the next question. Pause the video and have a go at this one. Alright then, so let's get going on this one then. Here is a solid bar made of metal. The bar is in the shape of a cuboid. The height of the bar is h centimeters. The base of the bar is a square d centimeters. The mass of the bar is m kilograms. D equals 8.3 to 1 decimal place. M equals, what's M? M is the mass of the bar. 13.91 to 2 decimal places, and h is correct to 4 correct to the whole number. Find the value of the density, give your answer in grams per centimetre cubed. So given that it's grams per centimetre cubed, that's given me a clue that I'm going to be doing mass divided by, well, actually it's mass in kilograms. So this mass here is going to be 13910 grams. I need to remember that, divided by centimetres cubed, so that would be the volume of the shape. So what we need first is a lower bound and then an upper bound. So the lower bound's calculation for the density is going to be 1390, so 2 decimal places here, 905 divided by, and then it's going to be the 8 points, so we want to divide by as much as possible here, 8.35 squared times 80, I want to divide by as much as possible, 84.5. So this bottom calculation here is the volume, and the top calculation here, that's the value of the mass correct to 2 significant figures, or the lower bound of it correct to 2 significant figures. So let's have a go at this calculation then. 13,905 divided by 8.35 squared times 84.5. And the answer to this is 2.360159339. And the upper bound would be 13,915, that would be making this 13.91 number as big as possible, divided by, now we need to divide by as little as possible now, 9.25 squared times 83.5. So let's just change a few of those numbers on my calculator screen at the moment. So that's now a 25. So yeah, that's now a 25, and this is now at 83.5. So let's divide the two numbers, and we get the answer of 2.44843646. So now both of these numbers, we need to choose a number that will round both of these numbers to the correct significant figures. And the answer to this question would be 2.4 to two significant figures. Because if I were to go to 3 significant figures, it would be 2.36 and 2.45, whereas both of them round to 2.4 to 2 significant figures. So the answer here is 2.4 grams per centimetre cubed to 2 significant figures. And there we are, that's the answer to this question. Okay, let's move on to the next one. Pause the video and have a go at this question. Okay, so let's have a go at this question then. So we're looking to find the upper bound of the value for m. So we want to start with as much as possible, that would be 346.65. We'd then like to take away as little as possible if we're looking to maximise the output, that would be 79.5. And then we're looking to divide by as little as possible to maximise the output, 5.25. So let's grab our calculator then and compute 346.65, take away C, that's 79.5, and then divide by 5.25. So grab the calculator fraction button, 346.65, take away 79.5, divided by 5.25, and that equals, we want to 3 significant figures, something sensible, 50.9. There we are, that's the answer to that question. Let's move on to the next one, pause the video and give this one a go. Okay, so in this question we're going to be using the formula speed equals distance divided by time. So the distance that the athletes will be running, if we're looking to find an upper bound, will be 400.5. Divide that by the time to the nearest 0.1 seconds, and if we're looking to find an upper bound, we're looking to reduce the time, so that's 50.15. So grab the calculator and 400.5 divided by 50.15, and that gives us an answer of 7.99. 7.99 meters per second, to 3 significant figures. Okay, let's move on to the next one. Pause the video and give this question a go. Okay, so a car travels a distance of 63.5 kilometers, correct to the nearest 0.5 kilometers. The car takes 45.8 minutes, correct to 1 decimal place. Work out the lower bounds for the average speed of the car. So again, this is speed equals distance divided by time, but we're looking to have our answer in kilometers per hour. So the first thing I need to do is convert 48.5, or the lower bound for this, into an hour, and then we've got this in kilometers. So it's going to be speed equals, we're looking to find the lower bound, so that's going to be 63.25 if it's to the nearest 0.5 kilometers. Divide that by, well, it's going to be 45 point, if we want to find a lower bound, we're looking to do as much as possible. Now this thing here, if we convert it into hours, we need to divide this by 60. So it's be 45.85 divided by 60. And that is 0.76416 with a little dot above it on the calculator. So this will be the amount of hours we're taking. So it would be 0.76416. So on the calculator, I'll now do 63.25 divided by answer button. And the answer to that is 82. To 1 decimal place, 82.8 kilometers per hour. So there we are, that kind of makes sense. If you've done 63.5 kilometers in about 3/4 of an hour, then it makes sense that you would do more in an hour. Okay, let's have a go at the next question. Pause the video and have a go at this one. Okay, so we're looking to find the lower bound of this calculation, so we want to start with as little as possible, 27.25. We would like to then take away as much as possible, that would be 18.5. And then we're looking to divide by as much as possible as well, so we'll call it 9.815. So the calculation is going to be t equals 27.25 minus 18.5 divided by 9.815, and grab your calculator. Let's do the fraction button. 27.25 take away 18.5 divided by 9.815 equals, the answer here is going to be 0.891 seconds. Oh, actually, you don't know it's seconds, but yeah, it's 0.891 seconds to 3 significant figures. Okay, let's move on to the next one. Pause the video and give this question a go. Okay, so let's have a go at this question then. So Jackson is trying to find the density in grams per centimetre cubed of a block of wood. The block of wood is in the shape of a cuboid. He measures the mass as 1,970 grams, correct to the nearest 5 grams. By considering bounds, work out the density of the wood. Give your answer to a suitable degree of accuracy. So this is one of those questions where you have to work out a lower bound calculation, an upper bound calculation, and then find a number that will round to both of these answers, correct to your nearest significant figures. So the lower bounds, we're going to try and lower this value here, and it's going to be grams divided by centimetre cubed. So it's going to be 1967.5, that was what the lower bound would be to the nearest 5 grams. Divide that by, we're going to be dividing by as much as possible, so it's going to be 13.25 times 16.05 times 21.75. And grab your calculator and work this out, and make sure you write down a lot of the decimal places afterwards. So 1967.5 divided by 13.25 times 16.05 times 21.75, and that equals 0.4253677546. Okay, time to move this up to the upper bound spot here. That's going to be 1972.5 divided by as little as possible, so 13.15 times 15.95 times 21.65. So fraction button, 1972.5 divided by 13.15 times 15.95 times 21.65 equals 0.4343328506. Okay, so now let's go for the answer. We're looking to find a number that will round both of these to as high a decimal place or significant figure as possible. Now 0.4 to one decimal place would be absolutely fine. What about, let's try and do this a little bit better. What about 0.43? Yes, 0.43 to two decimal places would be absolutely fine as well. So that beats 0.4 to one decimal place. So what about to three decimal places? Well, no. That would be 0.425 and this would be 0.434. That's different, but they would both round to 0.43 to two decimal places. So that is the answer to this question. In fact, we should write it out as 0.43 grams per centimetre cubed to two decimal places. And there we are, that's the answer to this question. Okay, let's move on to the next one. Pause the video and give this one a go. Okay, so let's have a go at this question then. So a train travelled along a track in 110 minutes, correct to the nearest 5 minutes. Jake finds out that the track is 270 kilometres long and he assumes that the track has been measured, correct to the nearest 10 kilometres. Could the average speed of the train have been greater than 160 kilometres per hour? Show how you're working to get you to your answer. So it's going to be speed equals distance divided by time. Now the first thing we'll need to do here is do speed equals, now if we want to maximise this speed, we're going to need to do 275 as our upper bound on the distance. But we also need to convert 110 into hours. But before we do that, we'll round it. So it's going to be 107.5. We're looking to divide by as little as possible here. So 107.5. When we divide that up into 60 to work it out in minutes, in hours I mean, gives us 1.7916. So when divided by 1.7916, so that's 275 divided by answer equals 153.48, 0.49. So no, it is not greater than 160 kilometers per hour. Because the maximum it could have been was 153.49 kilometers per hour. Jake's assumption was wrong. The track was measured to the nearest 5 kilometres. Explain how this could affect your decision in part A. It will not affect the decision in part A. Not affect decision. Because we'll be dividing by less. Because we would divide by less. Which will not increase the overall figure, the overall speed. Okay, so there we are, that's the answer to that question. Let's move on to the next one, pause the video and give this one a go. Okay, so in this question, correct to the nearest millimetre the length of a side of a regular hexagon, 6-sided shape that is 3.6 centimetres. Calculate the upper bound for the perimeter of a regular hexagon. So the upper bound would just be 6 multiplied by 3.65, because there are 6 sides on the perimeter. 6 times 3.65, and that equals 21.9. 21.9 centimetres. Correct to one significant figure, the area of a rectangle is 80 centimetres cubed. Correct to two significant figures, the length of a rectangle is 12 centimetres. Find the lower bound for the width of the rectangle. So we're going to need to do area divided by length here to get width. So the lower bound for the area is going to be 75, and the upper bound for the length of the rectangle to lower this overall output is going to be 12.5. So let's do the division there. 75 divided by 12.5. That gives us an answer of 6. 6 centimetres will be the lower bound for the width of the rectangle. Okay, let's move on to the next one. Pause the video and give this one a go. Okay then, so for each number then, let's work out the lower bound or the upper bound is appropriate. So 42 if we're looking to find the lower bounds overall, this needs to be as low as possible, so 41.5. On the value for B, we're looking to divide by as much as possible, so that means it's going to be 24.5. And for C, we're looking to take as little away from B as possible to maximise B, to maximise the total denominator. So actually C needs to be a lower bound, so 13.5 is the answer for C. So let's do the calculation then. Y equals 41.5 divided by 24.5 minus 13.5. Let's grab a calculator and work out the answer. 41.5 divided by 24.5, take away 13.5 equals 3. Give your answer correct to two significant figures. 3.8. I don't know what the units would be. 3.8 is the answer to that question. Lovely. Let's move on to the next one. Pause the video and give this question a go. Okay, so similar to the question before then, find the upper bound. So A is going to be 58.5. B is going to be, we're looking to decrease, work out the lower bound for the denominator. So we find the upper bound in total, so that's 27.5. And if we're looking to minimize the denominator, we're looking to subtract as much as possible. So that would be 18.5. So the value of this thing here is going to be 58.5. divided by 27.5 minus 18.5 equals, so let's grab the calculator, 58.5 divided by 27.5 minus 18.5 equals 6.5. And there we are, that's all the questions we're going to go through in this accuracy calculations video. Hopefully you found it useful, hopefully you've now understood what it means to be of a suitable degree of accuracy. And move on to the next GCSE revision video. Hopefully you found this useful. Thanks very much for watching.